Assalamualaikum warahmatullahi wabarakatuh, Doctor. My name is Ahmad Azim, and we from Group 7. We would like to present our project for the relay coordination. So before we begin, we show that this is our circuit, and we will ensure that our circuit will follow the specification that were given in the network data. The bus 1 and bus 2 supposed to be 132 and 11 kV. U2 11 kV, and then our underground cable 1 should be 240 and length of 300, same as for the underground cable 2. And then the transformer should be follow them. Running foot resistance should be 4 ohms and 30 MVA. And then for the relay, we use the specific branding based on this. For example, this one should be Siemens, and this one should be ABB, and this one should be Alstom. So we follow the circuit based on this specification. Okay, once we confirm our circuit, we will run the log flow simulation. In the log flow simulation, we will see the maximum load flow current for each relay. For example, this relay 1 will have 62.2 ampere, and relay 8 will have 759.8 ampere, and relay 11 will have 967.3 ampere. So this all value will be tabulated in our slide here. And that's all for the question 1. And move on to question 2. We'll run a short circuit analysis. So we will use this around 3-phase device duty to run our short circuit analysis. But before that, we need to turn on the fault for each buses. Already turned on, and then we run, and we can see the fault for each buses: 1.396 kiloampere for bus 1, and 116.17 kiloampere for bus 2, bus 3, sorry. And not only that, we also take the maximum fault current for each relay. For example, the relay 1 will have 0.272 kiloampere. So this same as before, this value we will tabulate into the table. This is for each buses, and then for the maximum fault current we will use for the calculation, so we need to tabulate too in our table right here. So that's all for question 1 and question A and question B.
Hi, my name is Andrew L, and now we proceed to part C, where we select the transformation ratio of the current transformer and the alternating the class P for the CT and the suitable accuracy limit current as is chosen. From the table mentioned in part A, the maximum load current is determined, and the CT ratio at which relay can be determined by choosing the value of the primary CT greater than the value of maximum load current. So the values in part A is used. Whereas for the secondary CT, 1A is chosen, and the accuracy limit factor can be found by taking the ratio of fault current, which is determined in part B, with primary CT, and the standard value of AIF must be followed since it is rated at 5, 10, 15, and 20. The accuracy limit current can then be calculated from the product between the ALF and the rated CT secondary current, which is 1 ampere. And the cask accuracy chosen will be 5P as mentioned just now, and the formula calculation is used here. So the maximum load current is for relay 13 is 93.5 kiloampere as determined in part A, and when fault is at bus 5, the fault current at relay 13 is 0.647 kiloampere as is determined in part B. So here for the CT, we chose 550 as it exceeded the maximum load current of 93.5, and the LF calculated is 4.31, is less than 5, so therefore 5 is chosen, and the LC is 5 ampere. For the class, in the end is 5P5, and is because 5 is chosen because the LF calculator is less than 5, 5 is chosen for the reliability of network protection, electrical protection. For maximum current at relay to relay 12, 642.8 kiloampere at relay 12, and when fault is at bus 5, the current at relay 12 is 3.603, 603 kiloampere. The CT chosen is 700 as it need to exceed the maximum current at 600, and calculated ALF is exceeded 5. Therefore, 5 is not reliable anymore. Therefore, the next thing we choose is 10. ALC chosen is 10 ampere, and the class is 5P10. So we can key in these values by clicking on the CT, 150 to 1, 5P5 for relay 13, and for relay 12, 700 to 1 and 5p10 for the class designation. So this continues for relay 11 as well. 750 exceed this value, 697.3. And the error calculated is 5.2, therefore 10 is chosen, ALC 10 ampere, 5p10. And for relay 10, 62.7, therefore CT chosen is 100 instead of 100 is chosen. The LF calculated is 4.33, it's less than 5, therefore 5 can be chosen. And the ALC is 5 ampere. So for the class, it's 5p5. And this is the same for relay 9 as well. 800 is CT is exceeded for the value, and the AR calculator is exceeded as 5, so 10 is chosen. ALC is 10 ampere, class is 5p10. And for the maximum load current, CT is 800 because 800 is bigger than 759, and this continues for. And the ARF is calculated is 5.32, it exceeded, therefore 10 is chosen. This is the same for relay 7 as well, 800 to because it's larger than 735, and for ARF, 10 is chosen, exceeded 5. Is for relay 6 also the same as well. All the values of the relay can be inserted into the CT by clicking on the CT respectively, 800 to 1, 800 to 1, 5p10. Actually, most of them, all for relay 6, 7, 8, 9, all of them are 800 to 1 and 5p10. As we see here, 800 to 1, 5p10. So now we move on to relay 5. The maximum load current calculator is very small. And when the fault at bus 2, the current at relay 5 is 8,056 ampere. So the CT chosen is very large compared to the maximum load current. As for the LF, we need to calculate where it's less than 20, less than the value of 20. Because if the LF exceeded 20, the secondary current in the CT will be distorted, and the protection of the electrical network will be unreliable and cannot be dependent. So therefore, we have to pick a very large primary CT in order to reduce the LF. In here, we reduce it to 16.11. So 20 can be picked, and ALC of 20 ampere, again class 45P20. So now we can can insert all these values into the CT here. This is the same for calculation. Relay 4 and relay 3 have the same fault when fault is at bus 1, they have the same current, again 3.911. And after calculation, 800 is chosen because it has to exceed the load current, the large load current of 746.7, class 5p5 because it's less than 5, therefore 5 can be chosen. It's the same for relay 4 and 3. Therefore, they both have 800 to 1, 5p5, and 800 to 1, 5p5. As for relay 2 and 1, they have a small load current. 100 can be chosen as because the LF calculator is less than 5. Therefore, LF 5 is chosen. And this is the same for both because they have the same parameters of the maximum load current and the fault current in relay 1. Therefore, now you can also insert these values in them. 100 to 1, 5p5, and 100 to 1. 100 to 1, 5p5. Now this is the table comprising of all the maximum load of all the CT ratios selected and the accuracy limit factor. So now we move on to the part D.
So hi everyone, today I'm going to explain how to calculate the ETAP setting and time dial setting for our relay. So as we can see here, we have 6 formulas over here. We have plug setting over the maximum, load current over the CT ratio time 100. We have RSI, which is we get the CT ratio time the plug setting that we did just now. And then the PSM is the fault current over RSI that we get just now. And then the RCOT is over 0.14 over TSM of 0.02 minus 1, TSM that we get just now. And then TSM of the relay is ROT over RCOT. As we can see here, ROT of relay B is equal to delay time plus ROT of relay B, relay A of the previous relay. So we assume relay delay time is 0.4 for this project. So we want to calculate the DU and TSM of the relay 10, relay 11, relay 12, and relay 13 is actually the same because it has the bottom part of the network. So as you can see here, the relay 12, the plug setting is must be larger than 62.33. So we choose 75%. So it's larger than this one 62.33. So because we want to have a safety margin between the relay. And then the ROT, as we can see, we calculate RSI, PSM, RCOT using formula. And as we can see here, TSM we assume that 0.1 for all the bottom relay. And ROT we calculate, and then we use the RCOT times by TSM, and we'll get 0.3932. But for this relay, we ignore, because ROT at relay 9 and relay 12, which is relay 12 over here, is greater than relay 13. So as we can see here, P as a setting over here must be larger than 91.82. So we choose 150 We calculate RSI, PSM, RCOT, and then as you can see, TSM also we assume at 0.1. And then ROT, as you can see, ROT of relay 12 is larger than ROT at relay 13. So moving on to relay 11 and relay 12, we calculate both the setting, and then it must be larger than 92.97 for relay 11, so we choose 150. For relay 10, it must be larger than 62.70, so we choose 75%. We calculate RSI for both relay, TSM for both relay, RCOT, and as you can see, we assume that TSM for relay 11 and relay 10 is 0.1. So ROT for both relay, we calculate using RCOT that we calculate, and by the assumed TSM, and then we will get 0.558 for relay 11 and 0.923 for relay 10. But we will ignore the relay ROT at relay 8 and relay 10 because it's greater here. Relay 11 is greater. Then we're moving on to relay 9. Relay 9, as you can see, we have relay 12 and relay 13, but we choose relay 12 punya And then here, as we can see, we get 0.50 at 0.560 at equal to 0.90 at. And then PSM relay, we use the PSM relay, we calculate RCOT, and then we will calculate PSM. And at relay 9, the plug setting must be larger than 91.89. So we assume that we select the plug setting 150, and we calculate RSI, RSM, RCOT, and then ROT, as you can see here, we use the RCOT multiplied by TSM at relay 9. So we get ROT 0.841. So moving on to relay 8, we have relay 10 and relay 11. As we know that we use the relay 11 because better, giving ROT, so 0.558, and then we will get 0.9558. So PSM, we calculate PSM, we calculate RCOT, then we get PSM of relay 8, which is 0.1630. 0.1640, and then the plug setting must be larger than 94.98, so we select 150. RSI, we calculate PSM, RCOT, and ROT, we use RCOT multiplied by PSM. Then we're moving on to relay 7, the plug setting must be larger than 91.89, so we select 150%. And then we will calculate RSI, PSM, RCOT, ROT. As relay 7 and relay 9 is series, jadi so they don't have any load. So we use PSM for relay 9 and relay 7 is the same. Same goes for relay 6. It's the same as relay 8 because there is no load over there. So but on the PSM for relay 6, we choose because it must be greater than 94.98. So we choose 150%. We calculate RSI, PSM, RCOT, and ROT. And PSM we choose from the relay 8. So it's the same like relay 8. Next one we go for relay 5. Relay 5. So relay 5 here we have it happened between the bus 2 and bus 3, right? So we have to calculate both ROT at when there is fault at bus 2 and bus 3. But here we only show you the highest one, which is at bus 2. So we calculate the ROT at 0.898, and then we will get 1.2898. Then we calculate PSM, RCOT, and TSM, then we will get 0.56 at 7. The plug setting, it must be higher than 6.94, so we will get 10%. Then RSI, then PSM. As you can see, for PSM at relay 5 is a little bit higher than the graph. So we must choose which the maximum value of the graph, which is 20 for PSM. So we substitute 20 into the RCOT formula, we will get 2.2673. Then we calculate our ROT, then the TSM will be 0.62709. For relay 4, we will using relay 4 and relay 3 is the same. It's the same, the calculation. And then this is we get for relay 5. And then PSM, we calculate PSM, we calculate RCOT. Then for TSM and relay 4, we will get 0.39956. For plug setting, it must be higher than 93.34, so we choose 150%. So we calculate RSI, PSM, RCOT, ROT. As we can see, we calculate using this formula. And we use this darab dengan PSM at relay 4, and then we will get TSM 0.39956. Same goes for our relay 3. As you can see here, we at our relay 5 and relay 3, we use 0.4 plus 1.0441. And then we PSM at relay 3, we calculate the PSM, we calculate the RCOT and TSM. So TSM at relay 3 is 0.39956. So as you can see, the plug setting must be larger than 93.34. So we select 150%. And then RSI 150 divided 100, we get 120. PSM, we calculate RCOT. Then ROT is 5.8850 times this PSM, we will get 2.3514. Then moving on to the relay 2. So what happened when there is a fault at bus 1 and relay 2, for relay 2 and relay 1? So for relay 2, we will calculate using the relay 4 punya ROT, then we will get for ROT for relay 2 is 2.7414. Then we calculate PSM, RCOT, and PSM for relay 2 is 1.4953. And the plug setting, as you can see here, it must be larger than 62.2. For a safety margin, so we have a safety margin, we choose 100% for the plug setting. And we calculate RSI, PSM, RCOT, and ROT. So ROT, we calculate RCOT multiplied by the PSM of relay 2, we get 10.356. For relay 1 is together with relay 3 so we calculate this is our ROT of relay 3. Then we time by the delay time, we get 2.7514. And this is the PSM, the RCOT, the PSM for relay 1 is 1.5953. And as we can see, the plug setting must be greater than 62.2. So we select 100 RCSI, we calculate PSM, RCOT, and ROT, we calculate the RCOT multiplied by PSM of relay 1, we get 10.356. So this is the conclusion for the plug setting and time dial part for relay 1 to relay 13. Okay, there's a lot of relay. So this is the time dial. So how you want to edit the relay at the ETAP? As you can see here, you can select your pickup current, and you can select your pickup time dial. You calculate, and then you set this here at all relay based on the table. That's all from me. Thank you.
Okay, so for this part E, we have to produce time current coordination curve of the relays on the system. Okay. So based on this software ETAP, we have to go to start the options, that is start protection coordination, which we switch the current presentation to star mode, and then we switch to star system to see the graph. Okay, so this is the time current coordination curve. To plot and display the grid. Okay, so based on this boot plot, we can see that for this vertical axis, this represents the time in seconds, and for this horizontal axis, this represents the multiples of rated current. Okay, so This is the curve for relay 1. Here, relay 1 curve, relay 2 curve, also here. Relay 4 curve, relay 5 curve, relay 6 here, it's relay 6, relay 7 is down here, relay 8 is here, okay, relay 9, relay 10 curve, relay 11 curve, relay 12 here, relay 13. Okay. Okay. So basically long time trip value will respond to overload or overcurrent, while short time trip and instantaneous trip will respond to short circuit. So all this relay characteristic is shown in standard inverse characteristics. So it is called IDMT relay, which the operating time is approximately proportional to the fault current. So I think that's it for part E.
Assalamualaikum everyone, my name is Anas Marani bin Ramli, and today I would like to present our simulation assignment part F, which is a sequence of operation for fault at each bus. So basically this is our simulation in our ETAP. So the fault occur at each bus. So when fault occur at bus 5 here, we want to know what relay operate first to withstand the fault. You can see here the relay 13 will operate first, followed by relay 10 and relay 7. We have ROT here with relay operating time here, which is 0.39 for relay 13, 0.5 for relay 10, and 0.46 second for relay 7. The relay operating time at each relay for fault at bus 5. Then next for the bus fault at bus 4 here, so we can see the relay 10 operate first with 0.39 second, relay 13 0.41 second, and relay 6, which is roughly about 0.5 second. Seems like in calculation we did at part B to get the ROT value. Next, for the bus 3, you can see the relay 13 operate first with 0.39 operating time, relay operating time, relay 10 0.397, and relay 11 with ROT 0.564, seems like we calculated before at bus 3. Next, for the bus 2, we can see here the relay 13 operate first, followed by relay 10, and then relay 11 with value of ROT here. Seems like in calculation we did before. And last but not least, when fault occur at bus 1, you can see here the relay 13 operate first, then followed by relay 10, then the relay 11 here to withstand our fault. Okay, that's fault at each bus. Then we can see here, this is when fault at bus 1, we can see, as I told earlier, at the ETAP simulation, which is just the same thing, at the bus 1, the bus 2, bus 3, bus 4, and bus 5. Okay, as for conclusion, the simulation of this ETAP very useful at the load flow, the short circuit analysis, the transaction of CT ratio, the time current coordination curve, and also the correct sequence of operation for fault occur at each bus was justified by obtaining by the value of the parameter like CT ratio and time settling with a reasonable explanation. This is very important to set up the delay of the interval because when fault occur, we have a backup and withstand to a certain amount of fault before its delay operating time. The purpose of this to prevent all the relay trip at the same time that can shut down our system entirely. So the maintenance should be done by at the CT or the relay that is always in good condition when there have a fault occur in our system. That's all from group 7. Thank you.